And battery degradation fundamentally is extremely difficult, and for a number of different reasons. But let's take, for example, the time and cost. It's quite typical that even for a small degradation study, you're in the 150, 200,000 pound range. And for OEM level degradation studies, they quite easily rack into the millions, even the tens of millions of pounds. And the problem is you have to wait 2 years to get the results. So a lot of the time, if you're developing a new product, especially on a new chemistry, it can take you a long time to actually get some indication of, whether that's actually going to meet the lifetime you require. Test matrices, are actually very hard to design. And a lot of the time, per matrix design, you don't actually realize until several years in. And the key thing to understand is data does not equal information. Just because you have loads of data on a cell, Rich is going to present later about how you actually want to gain as much insight as you can from that data. And so there's this disparity between both of them. The setup and safety of this is extremely expensive and difficult because of the safety implications. So there's a lot of expertise required in rig design, designing things for thermal runaway testing. And finally, there's a lot of resource goes into processing the data and ensuring it's of good quality. And fundamentally, if you're going to be making decisions based on degradation data, such as building a degradation model, it's really dependent on the quality of that data. And quite often, temperature errors, say from a thermal chamber failing for a few hours or the cells going out of the temperature window, can actually completely invalidate that data. And you might not realize for several months or even years after you collected it. So here's an example exactly of that, of a temperature for a cell under test. So this is for the moly cell P45B. So we've done 2 experiments here, one where we put the cell in a thermal chamber. So the cell's in like free air convection where we control the air temperature at -5 degrees. And you can see here the lines in red where the cell is actually heating up very rapidly through a drive cycle. So because of the resistance of the cell, it generates heat, and actually this cell actually has a very low resistance. So for energy cells, this temperature rise would be even greater. But here you can see in the green line, we use this Peltier element controller, which is able to actively cool the cell through conduction. And it's able to maintain the green line, which keeps the cell at -5 degrees. So on the left-hand side, you can see a cell where we make the electrical connections using these 4-wire Kelvin connections on either end. And then we use these conduction plates with Peltier elements to control the temperature, the surface temperature of the cell throughout the degradation.